This screencast will cover 3 topics. It'll review the 3 primary subatomic particles. It'll review the 3 common types of radioactive decay. And it will review the math on how you convert the percentage of individual isotopes to find the weighted average or atomic mass of a particular atom, and the reverse of that process. And also it'll talk a little bit about why knowing something about isotopes is very important in the geopolitical context of today. And we'll use the uranium isotopes to talk about that. So first of all, looking at this particular chart right here, you'll notice that we have our protons and our neutrons and our electrons. You're very familiar with those, probably from previous classes. The word proton, it's nice to think of the prefix pro as meaning positive, and the prefix neutron as being neutral, and then electron would be the negatively charged particle. Notice that the positive charge, its magnitude, is equal but opposite to the magnitude of the negative charge. Also notice that the protons and neutrons occupy the nucleus, whereas the electrons do not occupy the nucleus, but the electrons are in orbitals or shells. Back in 8th grade, maybe you had concentric circles, but they are in prescribed locations outside of the nucleus. We should mention, of course, that the protons and neutrons are also in a prescribed, organized fashion inside the nucleus. We don't know nearly as much about the organization of the nucleus as we know about the organization of the electrons about the nucleus. Some of the language that's used in talking about the organization of the electrons about the nucleus would be main energy levels, sub-levels, S, P, and D, and F orbitals, and electron spins within those orbitals. That's the part of chemistry that's often called quantum chemistry. Now, as far as the relative mass is concerned, if we assign a mass of 1 to the electron, you can see that the mass of the proton, the mass of the neutron, are almost 2,000 times greater in mass. But even more importantly, when you look at these numbers, and hopefully you notice this right off the bat, that when we add the relative mass of an electron to the relative mass of a proton, we get the relative mass of a neutron. And what this tells us is that a neutron, I use the letter N as a symbol there, can decay into a proton and an electron with its little negative charge, proton positive charge. The mass number of a neutron is a 1. The mass number of a proton is a 1. Mass numbers are made up of the total number of protons and neutrons, and electrons are not protons or neutrons, so it has a mass number of 0. The charge on a neutron is 0, charge on a proton is 1, the charge on an electron is -1. So please notice that, if I change colors here, that the charge 0 equals 1 plus a -1. And the mass numbers also equal on either side of the arrow. 1 equals 1 plus 0. Now, you might ask, how long does it take for a neutron to turn into a proton and an electron? And the answer depends upon where is the neutron. If the neutron is a free neutron, by that we mean it's outside of the nucleus, that neutron can last in that unconnected state between 10 to 15 minutes. In other words, it has a very short half-life, which makes it kind of difficult to measure precisely, and very easy to be affected by the systemic errors of the experimental process by which you measure the half-life of a neutron. The neutron inside the nucleus of an atom is extremely stable and can exist theoretically for billions of years. Next, you'll notice that we have the symbols, protons, neutrons, and electrons, and notice the little charge numbers. And notice that we use letters of the alphabet that seem to make no sense at all. So when we talk about an atomic number, beginning with the letters A and N, for some reason we use the letter Z. And of course the number of protons is the same as the number of electrons in a neutrally charged atom. The mass number, which is not to be confused with the atomic mass. The atomic mass is the weighted average of the isotopes. The mass number is exactly that. It is an integer, a whole number, beginning with 0 for an electron. And the mass number is going to be found by taking your total number of protons and neutrons and subtracting the number of protons, giving you the number of neutrons. Finally, and very important, you should know that if you change the number of protons, you get an entirely different element. So anytime you want to make a new element, all you have to do is take an existing atom of that element and either add or remove somehow a proton. That, of course, is not a chemical process, but a nuclear process. If you want to change the number of neutrons, you get an entirely new isotope. And some atoms can have 12, 14, 16 different isotopes, only a few of which would be very common and would be very stable. Most of the isotopes for almost all of the atoms, and if you add up all of the isotopes of all of the atoms on the periodic table, you have hundreds and hundreds of them. Most of those isotopes would be unstable, meaning that they would be they would undergo radioactive decay very quickly. And then if you change the number of electrons, you have a whole different ion. Now, if you have any questions about this, make sure you ask me in class for specific details. Moving on to the next page. The three common types of radioactive decay are alpha, which happens when an unstable nucleus shoots off a helium nucleus, or the equivalent of a helium nucleus, which would be 2 protons and 2 neutrons, hence the number 4, 2 plus 2. Or an unstable nucleus can shoot off what we call a beta particle. That beta particle looks exactly like an electron. You can call it an electron, but it's an electron that did not exist 1 minute, and now it exists the next minute, or you could even say second, or fraction of a second. It comes into existence and very rapidly is going to be captured by some other atom in one of its outer shells. Now, a gamma particle technically is not a particle, it's a high-energy photon. Gamma photons can go right through you and me. High-energy gamma photons can go right through the Earth. And we use this symbol right here. So these are the first 3 letters of the Greek alphabet: alpha, beta, and gamma. That's what the symbols look like. Some science fiction shows will suggest that maybe there's another kind of radiation that we haven't discovered yet, like delta radiation. The charge of the radioactive particles, for the alpha particle, it would be a 2 plus because it is a particle that has 2 protons and 2 neutrons. For the beta particle, it would be -1 because it's the same charge as an electron. And photons, high-energy photons, any type of photon, as a matter of fact, is going to have 0 charge. Now, the relative mass, alpha particles are very, very massive with respect to or in comparison to electrons, beta particles. And of course, photons don't have any mass at all. Now, as far as the ionizing ability, what we mean by ionizing ability is the ability to ionize an atom. So an alpha particle, which by comparison is big and massive, when it smashes into an atom, it can do a whole lot of damage. It can knock that atom into all kinds of charged pieces, so it has a high ionizing ability. Beta particles, their ionizing ability is much more modest. They're very small, but they do have mass, so we can rank them as medium on the low end, not halfway between high and zero, but on the low end there. And then your photons are going to have the lowest ionizing ability at all. If you think about an atom, the main constituent of the volume of an atom is nothing, is empty space. If you were to put a, say, ping pong ball at second base of Busch Stadium, the nearest electron might be a dot or an extremely small BB in the bleacher seats, and everything in between would be nothing, empty space. So you can see why a high-energy photon, a gamma ray, has very little likelihood of actually striking anything significant, since most of the atom is empty space. Whereas a big massive particle like an alpha particle has a high probability, in comparison, of striking an atom and messing with it, doing some damage to it. Now, because the alpha particle is so big, it doesn't travel very fast, and its penetrating ability is on the low side. Whereas a photon has so much energy, its penetrating ability is very, very high. You can kind of imagine, if you will, a little shop on a street or in a mall that sells very, very delicate china and glassware and pottery and vases and so forth. And a gamma ray would be like, what if some light were able to enter through a window or door and strike some of that delicate pottery? It probably would have very, very low likelihood of doing any damage. Now let's imagine a bee, in this analogy that would be the beta particle, a bee flying in through a window or a door. It might have a chance, if it was big enough and clumsy enough, to bump into something very, very delicate and maybe knock it over and break it. Now, the alpha particle, in my fictitious analogy, would be like, what if a bull, a big animal, or a moose or bear or something happened to find its way into the china shop? Well, just by virtue of walking around and moving around, it could do a tremendous amount of damage. So it's unlikely you're going to get a bear anywhere near a china shop, much less likely than a bee or light will enter, but boy, could it do a lot of damage. All right. Considering the fact that the number on a periodic table that is not a whole number, but has 4, 5, 6, 7 decimal places, that's the weighted average, the atomic mass of the isotopes of that particular atom. And when we talk about the unit, sometimes we use the letter U for an atomic mass unit. Sometimes we use the letters AMU for atomic mass units. And sometimes we call it the Dalton, naming it after John Dalton, 200 plus years ago, a teacher, began his teaching career when he was a teenager, and devout Christian, as well as a person who's devoted much of his life to his hobby or fascination of the weather, and recorded thousands of observations of the weather day after day after day. In any case, be aware that you can use any one of these symbols to represent an atomic mass unit. Now, if we think about neon, where did that number in red on the periodic table come from? At least it's red on the periodic table hanging in my classroom. And that number comes from the weighted average of its three isotopes. So if one isotope occurs in great abundance, we're going to weight that particular mass the most. And so neon 20 has a mass of about 20, as you might expect. Neon 21, here's neon 20, neon 21 has this mass near 21, and it also has a much, much lower percentage, the lowest of the three isotopes. Neon 22, with its mass near 22, has a higher percentage than neon 21, but nowhere close, about 10 times less than the abundance of neon 20. So they're going to be weighted differently. Now you might ask this question, why are the masses of a particular isotope not whole numbers? Well, here you have to keep in mind that it depends upon how this unit, what is one atomic unit, how that's going to be defined, but also on the fact that within the nucleus, protons and neutrons, some of their mass, if you will, is used up in holding the nucleus together using this famous equation right here. And that's the nuclear energy that holds the nucleus together that is released in nuclear reactions. So some of that mass is no longer in its mass form, but it's in the energy form. Now, when we do the math, you can do it as percentages, where you convert your percentages into decimal equivalents ahead of time, or you can multiply the percentages times the masses, and then at the end of the problem, divide by 100. So you can either divide by 100 up front or divide by 100 at the end. In this problem, we took the percentage times the mass, plus percentage times the mass, plus percentage times the mass, and these are added together. Now, please notice, as far as significant digits are concerned, we have 4 significant digits here, 3 significant digits there, 3 significant digits there. Notice now then I have 4 significance there when I divide by 100, because 100 is an exact number by definition. 3 significant digits, by the way, some people use significant figures, and 3 significant figures here. Now I'm multiplying by 5 significant figures, 5 significant figures, 5 significant figures, so I have to round off to the least number of significant figures, which is 4 and 3 and 4. And then when I go to add these numbers up, I round off to the least precise column, which in this case is going to be a 7 in the hundredths place. And now I have an answer that's in 4 significant digits, even though some of my original numbers, like this one and this one, only had 3 significant digits. This number, by the way, in the box, may or may not be what you see on your periodic table, someplace online or in a book. It all depends upon the precision of the measurements being made by the people who originally constructed the periodic table and then published it. So many different organizations have a periodic table, and that periodic table could vary a little bit, sometimes in the hundredths place, perhaps in the thousandths place. Now, we can also go in the opposite direction. If we have 2 isotopes of boron, and we know that the atomic mass of one isotope, boron 10, is near 10, and boron 11 is near 11, and then we look in the periodic table, and we see that its weighted average is 10.81, we set our math problem up exactly the same way as we did before. We do percentage times mass plus percentage times mass equals percentage times mass. And don't forget this 100% here. And since we only have two isotopes, one isotope has X%, the other isotope has 100 minus X%. And therefore, we have only one variable. And now when we go through and do our math, paying attention to significant digits, here you'll notice that I have 2, 4, 6 sig digs there. I have 7 sig digs there. I have 4 sig digs there. I keep those sig digs down here. But now when I add or subtract, you'll notice that this 4 sig digs only goes to the ones place. I have to keep that in mind. I'm going to be rounding off to the ones place eventually, because this only goes to the ones column. And so later down here is where I round off to the ones column. Since in this math problem, the ones column happens to have a 0 in it, I show that it's significant by using the decimal point. Remember, in terms of significant digits, 20 does not equal 20 with the decimal point. This has one significant digit. This has two significant digits. And so you can see that my weighted average, which if you look up here, you can see the weighted average of 10.8 is closer to boron 11 than it is to boron 10. And sure enough, I have 80% boron 11, so it's going to be the bigger contributing factor to the weighted average, and only 20% of boron 10. Here's another example using chlorine. Now, I should point out the fact that most of the time you're going to have more than 2 common isotopes. You can have 3 or 4 common isotopes, for example. By common, I mean relatively stable. And when you have that situation, you're not going to use X and 100 minus X, but you're going to have another equation in there, something that's going to relate. Let's say you have X%, let's say you have X%, Y%, and Z% of 3 isotopes. You're going to have some way of relating X and Y, and one way of relating X and Z. In this particular case, we're relating, if this is my X, my Y is 100 minus X because I only have 2 isotopes. But if I throw in a third isotope, isotope Z, then I'm going to have some way to connect Z to either Y or X isotopes in order to continue with this math. Now, the last thing I want to do is talk about why it's important to know something about isotopes and why I wish the people in Congress and the Senate and our government knew more about isotopes. And that is because of the proliferation of nuclear weapons. Nuclear weapons are weapons that involve, right now, either splitting the nucleus, which would be a fission reaction, such as in the atomic bomb, which uses uranium or plutonium, or fusion reactions, also called hydrogen bombs, which involve fusing hydrogen together. And our big concern right now is not with the fusion hydrogen bombs, but it's with the easier to make and launch and use nuclear atomic bombs. And there are 2 main elements that you can use to make a nuclear bomb, as well as to use as fuel in a nuclear reactor. And that's going to be plutonium and uranium. These are the only 2 elements that are in significant abundance enough to be able to make to fuel a nuclear reactor or to make a nuclear bomb. The nuclear bombs that were dropped in Hiroshima and Nagasaki in the summer of 1945, one was a uranium fission bomb, one was a plutonium fission bomb. And they both used different engineering, different designs in order to explode and produce the extraordinary energy that leveled those two cities and ostensibly basically ended World War II with Japan. Now, it's also important that we not think that nuclear reactors are anything at all like a nuclear bomb. It is physically impossible for a nuclear reactor to blow up like a nuclear bomb. You can have other issues in a nuclear reactor, like a meltdown if the coolant, the cooling water is somehow not able to remove all the heat. And then you end up with a big mess, as well as potential of some radioactive steam that would be dissipated in the environment. And the reason for that is as follows. When we dig uranium out of the earth, and you can find uranium in probably any shovel full of dirt anywhere on the planet. But of course, whatever metal we're trying to mine, we always mine it in a place where it's in high concentration. That's true for iron or copper or cobalt or anything else. So we look for a place where there's a lot of uranium compared to normal, ordinary places where we wouldn't bother to mine. And when we dig uranium out of the ground, natural uranium is almost all 99.3% uranium-238. And then there's a much smaller amount of uranium-235, about 0.7%. And technically speaking, there is another relatively stable isotope of uranium, uranium-234, with its 142 neutrons, and that's really not worth talking about in terms of its abundance. So I'm going to limit my discussion to uranium-238 and 235. Now, when we dig this uranium ore out of the ground, and we want to use it in a nuclear reactor like Callaway here in Missouri, about, an hour and a half or so, hour and 45 minutes west of here on I-70 towards Columbia. What we need to enhance it or enrich it up to 5%, let's say. We want to go from ordinary 0.7% up to 5% uranium-235. And the way that we do that is by removing the uranium-238 atoms. Just like in the classroom, we could increase the percentage of girls in the classroom by removing some of the guys. Here, if we can remove some of the uranium-238, we can increase the percentage of the uranium-235. And we do that through a centrifuge, gaseous centrifugation. We basically combine the uranium with fluorine gas and we make uranium hexafluoride gas. We put it in very, very high-speed centrifuges and spin it. And as we spin it, the more massive lumbering uranium-238 atoms, or in the form of U-238 F6, uranium hexafluoride, flies off, and the uranium-235 stay put, and we increase the percentage. Now, by the way, that the uranium-238 is not useless. We can actually use uranium-238 to make plutonium. And if I can go on off in a brief tangent here for a minute, the thing that why do we want uranium-235 and not uranium-238? Because when we take uranium-235 and we hit it with a neutron, we've got to slow the neutron down a little bit, but when we hit it with a neutron, the uranium is going to split. And we're also going to get a few extra neutrons, 2 or 3 neutrons, which can keep the chain reaction going, and we're going to get a whole lot of energy. And we're going to talk more about what these daughter products of the splitting of uranium-235 are in the unit on nuclear chemistry later in the book. Now, if we have uranium-238, let's pick a different color, and we hit that with a neutron, it just turns into uranium-239, because a neutron is one mass particle. And you might say, well, uranium-239 is boring. Well, not really. uranium-239 can undergo a double beta decay, and again, that's for a later chapter. And a double beta decay actually turns uranium into plutonium, and plutonium, when you hit it with a neutron, will split, so it can be another fuel in a nuclear reactor. And this process is involved in what we call breeder reactors, which can take uranium-238 and convert it into a fuel, almost an inexhaustible fuel, because we have so much uranium-238 compared to uranium-235 to run nuclear reactors with. Now, that's all beside the point. Back to my concern about the proliferation of nuclear weapons. If you want to have a nuclear bomb, you need to get up over 90%. So that's a big difference to go from 5% to 90%. That means you need lots and lots and lots of high-speed centrifuges. And somewhere more than 10 years ago, I don't remember the exact year, Iran was busy using their centrifuges to enhance their uranium, and they were at somewhere, I think they were around 20% or so. And all of a sudden they had a huge computer malfunction. A computer virus actually got into the workings of the hardware and wrecked all of their centrifuges and set them back a lot of years. Where that computer virus came from, everybody can, it would be a pretty logical to speculate that that was probably the work of the United States and especially Israel working together. But no one has ever actually declared that as far as I know. Now today, and I just saw this just within the last year, Iran right now is well over 60%, and may even be over up at about 80% uranium-235. And of course, I should mention the reason we need such a high percentage is because as soon as you blow up your uranium nuclear atomic bomb, all of the ingredients of that bomb are spread out all over the place, and you no longer have enough uranium in one place to sustain a chain reaction to keep the energy being produced like you do in a controlled reactor, where we can operate these reactors for years on end and generate electricity very, very constantly, except for periodic shutdowns to replace a few of the depleted fuel rods. So this is a very big concern because, of course, Iran has that stated objective that they want to destroy Israel, and they also hate the United States as well. The United States and Israel are sometimes called by this faction of the Muslim faith, the Great Satan, and that there's a very, very real concern of their developing enough uranium-235 enhanced fuel to create their nuclear bombs. And of course, they are very, very close to the country of Israel. And we should be very, very concerned about that. There's a reason why they are working 24/7 in deep underground with these centrifuges going. And they won't let people come and look at all of the places where this is going on. Anyway, by the way, one more time, remember there's a difference between the atomic number, the mass number, protons and neutrons, the atomic mass unit, which can be AMU, U, or Dalton. It's defined as 1/12 of the mass of a carbon-12 atom. And that, by the way, I recall, is a test question and can be a test question on an AP test. And then the atomic mass is the weighted average.